Ich habe nur, das Problem ist, dass du eine Dockingstation hast. Ich hoffe, dass der jetzt durchhält für die Stunde.
Also der Akku hält normalerweise, wenn ich den ohne Netz nutze, 10 Stunden.
Ja, dann passt das schon.
Wenn ich irgendwas Aufwendigeres mache, 4 Stunden, 5 Stunden.
Ja, geht schon. So, should be I give you a cluster.
Yes, I have to make an adjustment today. Which should be okay. Yes, because the 3 weeks for the circulation. But I have already submitted all the documents. Yes. So now, if you find out that today is ready, it's enough time.
Because it's 3 weeks after.
Yes. So it should be.
And you have contract.
I've been floating in the air for like 3 months.
And you are in the
Yes. So, yes. That's good. That's what's
yeah, but one number. Yeah, this
yeah, I got through it. So that's
Hey man, and finally also submitted or?
Yes. Done.
And this also the submission or like the acceptance for the 3rd of April it was?
Yes.
So you have to use them on the 3rd of April. Crazy, nice.
Yes. That was
very close call.
Very close call.
Great.
And also, it seems like I might not have to pay extra.
Yeah, okay. They say like I don't. Okay. 11th. But this like the date, like I thought that the date of the defense is mandatory, crucial for the semester, not to be enrolled.
Well, maybe.
Yeah, like
Because I spoke with this guy and he was like,
Entonces tengo 2 laptops. Ya me lo mandaste. Ja, vale. Lo voy a acabar ya. ¿No? Ese van a la no. Claro, estaba en la puerta por eso, porque para ver si porque no sé si puede conocer.
Sigamos que afuera, espera, que se lleve.
Ajá, sí.
Ja, danke. Ja, bitte schön. Did you get any feedback from the Prüfungsamt?
no, I'll go there in person to submit the CD and then when I'm about to collect.
Okay.
Aber funktionierende Schriften hier?
Ja, ich habe schon. Die habe ich ein bisschen länger, aber rot und schwarz. Die gehen.
Ja, die erste Frage. Sí.
What's the lead on so
Sì, perché non ci sono poi.
Ya, no, pero.
Nein, so eine generelle.
Nee, dann kann die Prüfung nicht stattfinden.
Ich habe das einmal gehabt, da haben wir in der Prüfung gesetzt und der Prüfer kam nicht. Und dann, das war bei Herr Ulrich, gesagt hat, ich rufe den jetzt an. Ging in sein Büro, kam zurück und sagte, er kommt sofort. Der Prüfer sagt, ich habe den Kalender gesehen, konntest du nicht mehr lesen. Und ich habe mir gedacht, wenn es wichtig ist, dann werde ich noch mal dran erinnern.
No, no pienso para más. Oiga, Hans-Peter, ¿no? ¿Qué es cuando necesito mi examen?
Das war jetzt wohl nicht möglich.
Okay. Ich habe nämlich nachher jedes Mal, wenn Hans-Peter eine Prüfung versäumt hat, nicht mehr ihn angerufen, sondern seine Frau, das ging schneller.
Ist das so die CC?
Ich habe das so in Dortmund von einer meiner späteren Doktoranden, der nicht so nervös da den Gang aufgekommen hat. Das ist so, ich habe gleich die Diplomprüfung. Dann kann die Mitarbeiter, bei wem machst du die Diplomprüfung? Ja, bei Professor XY. Das kann nicht sein, der sind wir nicht.
Das ist ja gut dann. Wird verschoben.
Ja, gut verschoben hatte. Der hat vergessen, dass er eigentlich an den Tag Prüfung hat.
War nicht mehr so nervös.
Aber
Und das ist sowieso einer meiner nervösesten Programme, den er erwähnt hat.
das ist aber echt dann bitter für seine Doktoranden. Also das ist mir völlig aufgelöst. Ich finde das ja schon schlimm, wenn die Prüfer zu spät kommen, dann ist man ja auch so hibbelig.
Ja.
Allein wenn die nur eine 10 Minuten zu spät sind, habe ich mir das Gefühl, die Prüfer, die stottern am Anfang noch, weil die deswegen noch so nervös sind.
Oha.
Noch 4 Minuten.
Ja, auf jeden Fall. 6.
Ah, da ist er ja.
Ja, ich bin so schön gemacht. Jetzt hat es voll geschlafen gestern Abend.
Hola.
Kannst du einfach einnehmen, die Fragen stellen oder soll ich dann auch
Kann ich machen, soll man sagen, lieber
mal? Das ist doch besser, ja.
Ich glaube, wir machen das.
Dann bist du gelandet.
Gestern Morgen. Nee, also ich war halt komplett raus.
Interesse, aber du hast ein PDF.
Ja.
Und der hat mir, du hast ein Interesse, aber sie schauen, wie es arbeitet. Nein?
Das ist PDF?
Nur die PDF.
Yeah. And yesterday I got an email from the PhD exam that I completed the thesis on Thursday, but I closed it to happen.
No, we have to return it together with the review. That's why I asked you for the PDF, because I knew I had to return it.
Oh, okay.
It's okay. That's why I need the PDF.
Sí, dice que no puedes escuchar.
Willst du noch die Tipps? Sind wir alle?
Hopefully, yeah, it's a lot of people. Yeah.
Okay, so welcome to this disputation, thesis defense of Yokari Loyola. As usual, the process will start with a 20-minute presentation from her side regarding what she did during her doctoral studies. And then after that, we will have a scientific discussion. And afterwards, I will ask everybody in the room to leave, so we will decide on the final grade. So, since it's 11 sharp, you can start. You have your presenter, everything's working, so stage is yours.
Thank you. Hello, everyone. Today I will present the research finding I obtained during my doctoral studies at the University of Munster under the supervision of Professor Strasser. Chromophores have a wide range of applications across various fields, including sensor, energy and data storage, photocatalysis, and OLED. However, in our research group, they have been mainly explored as fluorescent proofs, photosensitizers for photodynamic therapy, photothermal therapy, photoacoustic imaging, and even more recently, magnetic resonance imaging contrast agents. The design and synthesis of chromophores incorporating transition metal involve varying factors such as the choice of the metal ion and the type and number of primary and auxiliary ligands, which overall influence the properties of the resulting complex for the specific applications. As part of my doctoral studies, I managed to complete several projects that are related to the study of chromophores, which can be categorized mainly in two areas. One is the study of the influence of the asymmetry of tridentine chromophores on the photoluminescent properties of platinum-2 complexes, and the second one is related to conducting an extensive characterization of the excited state properties of the tetradentate chromophores known as ophthalocyanins, their nanohybrids with laponite, and explore their potential application for MRI. And I will start by discussing the tridentate chromophores. Several studies have shown that the incorporation of tridentate chromophores such as terpiditine favor planar and rigid environments that allow transitions arising from MLCT states that can be easily tuned by substitutions on the pyridine ring. However, these kind of complexes typically show weak emissions with poor photoluminescent quantum yields and short lifetimes. In an attempt to further enhance the virtues of the pyridine, Azole rings have been incorporated due to their strong sigma donating character that enhance the electron delocalization and increase the ligand feed splitting. In agreement, platinum-2 complexes containing these tetrazole moieties typically show emissions arising from MMLCT states due to self-assembled behaviors that favor the formations of fibers or gels under specific conditions. And these tetrazole moieties offer a further tunability of the electronic properties by substitutions in the azole ring. And this offers a further control over the color purity, and the self-assembled properties can be preserved. Despite all the extensive studies on this field, a systematic investigation between the combined effect of both tetrazole and triazole ligand rings into one asymmetric ligand are poorly understood. So the focus of this study is the design and synthesis of platinum-2 complexes incorporating the bis-tetrazole ligand and the bis-triazole ligand, functionalized with electron withdrawing and electron donating groups. The aim was to investigate how the electronic properties, along with the ligand asymmetry, could influence the overall behavior of the complex. The synthesis of the asymmetric complexes was conducted by some modifications in the already described procedure for the symmetric counterparts by reducing the equivalence or hydrazine monohydrate and shortening the reaction time. The obtained powder was further treated to obtain the R1-triazole CM precursor, which was then reacted, also based in the bis-tetrazole ligand, which was already reported, to yield the R1-triazole tetrazole asymmetric ligand. All the asymmetric ligands were reacted with a platinum precursor, and finally, amylpyridine was exchanged to yield the desired complex. And here are the proposed chemical structural formulas that were based on the NMR and mass characterization, as well as the nomenclature that we proposed. The emission spectra of the complexes at 77K show the typical vibrational progression for platinum-2 complexes, and all the emissions were observed in the blue region, following the tendency that you can see here. This tendency is in agreement with the one observed for the S0, S1 transition that was observed in the absorption spectra, which has an MLCT character. And this tendency is mainly driven by the electron deficiency of the tetrazole ring, which makes that the more blue emitter is the bis-tetrazole compound, and that all the asymmetric ligands complexes are blue shifted when compared with their symmetric counterparts. Regarding the electronic substitution, the electron withdrawing character of the CF3 substituent that stabilizes the HOMO increases then the HOMO-LUMO gap and causes more energetic transitions, as you can see here in the purple spectra. The opposite effect is then observed for the electron donating group terbutyl, which you can see here the spectra in blue. The asymmetry of the complexes proved to be a good strategy for improving the performance of the complexes, as proved by the compound terbutyl-triazole-tetrazole, which has a more red emission with a performance close to the one observed in the of the reference compound in the literature, namely BCF3 tetrazole. As expected, not all the findings of this project are applicable for the tetradentate systems, so I will continue by discussing that. These projects are based on the macrocycles of phthalate, which consists of 4 isoindole units that are linked by azomethyl bridges. They typically function as tetradentate dianionic ligands, and they have gained a lot of attention due to their outstanding photophysical properties that could go from fluorescence to phosphorescence or not emission. They have a very versatile chemical structure, and by changing the nature and oxidation state of the metal ion, as well as the substitutions of what are known the alpha and beta positions of the benzene ring, a lot of vast variety of compounds can be accessible. And all these modifications allow a fine-tuning of the properties. Despite all the virtues of the molecules, they have a strong tendency to form aggregates in solution that typically are not emissive, and they have poor solubility in a lot of common solvents, including water. And this two phenomena restrict their applications in a lot of areas, including biomedical applications and solid state. And we will see further in my presentation that explore and overcome this obstacle is a fundamental part of the research. The absorption spectra of the complexes show maxima between 650 and 700 nanometers with high extinction coefficients. As expected, the emission spectra are almost a mirror image of the emissive optoresonance with small red shifts. Among both set of spectra, some tendencies were observed. First, all the metal PC appear blue shifted when compared to the H2PC due to the lower symmetry of the H2PC, and among the DI metals, the platinum PC appears in the blue region, at shorter wavelengths. And finally, neither nickel or copper PC were emissive. And all these transitions were assigned to homolumen transition that occurred within the microcycle, as proved by the DFT and DDF calculations. And these results also were further supported by electrochemical studies. Although the triplet state formation was not observed under the previous experiments, we conduct transient absorption spectroscopy to confirm its presence. The spectra show broad absorption, positive absorption between 400 and 550 nanometers with maxima around 510, which can be assigned to TN-TN transitions. These species have lifetimes in the range of the microseconds, and they were drastically shortened after in the presence of oxygen. Additionally, all the spectra show at least two minima that are caused by the loss of molecules in the ground state. In agreement, these minima follow the same tendency that is observed for the absorption and emission spectra. By suppressing the vibrational relaxation of the molecules through the formation of frozen glassy matrices at 77 K, long-lived and intense phosphorescence was observed for both palladium and platinum PC. However, H2PC and zinc PC remain fluorescent due to the negligible intersystem crossing. Interestingly, an emission was observed for the system copper PC in the infrared region, however, with a short lifetime. In an attempt to promote a rigid environment that would favor the phosphorescence emission at room temperature, we decided to form PMMA fields. And the results of the photoluminescence experiments show that the fields show similar behavior to those of the frozen glassy matrices. So palladium and platinum PC show phosphorescence at this condition. And this new system allows us to further characterize the system in a wider range of temperatures, ranging from 6 to up to 300 Kelvin. In general, all the molecules show minor shifts in the emission maxima as the temperature decreases, as well as an increase in the lifetime. However, these changes were more prominent for the copper PC, a system whose excited state properties is poorly understood, and these motivate us to conduct further calculations to characterize its excited state. Although the ground state of the copper PC is a D0, the typical transition D1, D0 that will generate the emission of fluorescence should be around 660 nanometers, so very close to the other metal PCs. And the absence of an emission in all of our conditions for this emission prove that copper provides enough intersystem crossing to go to a quadruplet state. However, the fact that the poor intersystem spin orbital coupling of copper and the ophthalmosynine typical low metal perturbation in the excited state make that phosphorescence should be a highly forbidden process. However, the calculations show that there was an additional doublet state lower in energy that is available from the quadruplet of reference that could lead to a mechanism of spin flame activated delayed fluorescence. And this should happen by the absorption of energy from the D0 to the D1, followed by a intersystem crossing to the quadruplet state. From there, the molecule should have either internal compression or vibrational relaxation to the Q1 state, and from there the molecule could suffer either reverse intersystem crossing or spin flip to go to this doublet state, where the molecule finally will release decay by emission of fluorescence. The simulated spectra for this state resemble the ones obtained by our experimental conditions, and the theoretical the consequences of this mechanism would explain the prominent changes in both the spectra and the lifetimes. Although the emission of fluorescence by nickel PC was not observed by any of our previous experiments, it was possible to observe by an energy transfer mechanism by STM experiments. The typical non-luminescence of nickel is pretty well established that happens due to the fast intersystem crossing from the S1 state to a metal center state that decays in a non-relative way. However, the same happens when a monomeric nickel PC is excited by STM experiments, while the rest of the metal PCs show an emission of fluorescence that follows the same trends that were observed by our conventional experiments. However, when dimers were formed between a metal PC that is emissive and nickel PC, the spectra show always an additional band at lower energy that could be assigned to the emission of fluorescence by nickel PC. This behavior was explained by calculation and rationalized in the next way. The excitation of the metal PC favors a resonance energy transfer mechanism from the metal PC to the nickel PC, which get excited to a S1 state, however, to a low energy S1 state that we could call cold S1 state, which is lower in energy than the energetic barrier required for the system to undergo intersystem crossing to the DD state. Then the molecule from this cold S1 state has to decay by emission of fluorescence. And as I previously mentioned, the virtues of Laponines are limited, specifically in the biomedical applications, due to their poor solubility in water. So in our group, this nano composite that has a disc shape and is silicon based has been previously used as a carrier for non-soluble molecules due to some advantages such as biocompatibility, non-toxicity, and biodegradability. And so by the physician of Laponines of phthalocyanine onto the Laponines, we were able to obtain transparent water dispersible solutions that preserve the photophysical characteristics of those of the neat molecules in solvents, organic solvents. And interestingly, both palladium and platinum preserve both behaviors, fluorescence and phosphorescence. And this is caused by the heterogeneity of the medium. Additionally, highly concentrated dispersions of Laponine show a behavior known as thixotropicity, which means that they can form gels at rest due to a change in the density by self-assembled behaviors. And this allowed the obtention of the hydrogels, and we were very excited to see that the obtained hydrogels also preserve the emissive properties with just modifications in the emission spectra by self-absorption processes. Additionally, we were able to obtain the hydrogels for paramagnetic non-luminescent phthalocyanines, and these were evaluated as potential MRI contrast agents. And specifically, the ones obtained for the iron-3 phthalocyanine show relativity values comparable to those of the commercially available contrast agents for MRI. And with all that said, I just would like to highlight some conclusion about this project. In the case of the Trident Tech chromophores, we provide new synthetic pathways for blue shifted precursors that could allow the extension of accessible platinum-2 emitters and we improve the tunability and the performance on the complexes by mixing both the asymmetry and the electronic properties of the ligand. Additionally, in the case of for the tetrahedral chromophores, the change of the metal ion allows us to access different photophysical behaviors that range from fluorescence to phosphorescence, even at room temperature, and fluorescence in the infrared region or not emission at all. And this combined with some materials allow the obtention of different materials that could be applicable for dual functionality that will mix both behavior, photoluminescence, and MRI conference engines, enhancing the potential application of these molecules. And of course, this work wouldn't have been possible without all the contributions of many people. And so I just would like to thank my supervisor, Professor Strasser, my thesis committee meeting, Professor Nula, Professor Fernandez, my graduate program, my hosting university, all the collaborator partners, and of course my both research groups, my graduate program, and all of you.
Okay, there is opportunity to ask questions for those who have attended this defense. As usual, there is no so I will give opportunity to our guest, Professor Fernandez, to start with the first question round.
Okay, no problem. Yeah, thank you so much for the presentation. Maybe I can start. I have a few specific questions to the individual chapters. I don't know if you have the PhD with you.
I have a printed version.
Specific question on page 57. I'm curious about what is the origin of the broad transition in the UV spectra of the complexes.
57.
It's a chapter about the platinum complexes.
Yeah. Do I have the spectra?
Page 57, I think.
Yeah. Should I project the spectra?
Yeah, please.
I have it. I mean, I haven't support slides. I should have the spectra. I think so. Yeah, here. These are the
Yeah, there's a minor but broad absorption for all the complexes. It changes the wavelength depending on the compound. Yeah, that one. What is the origin of that?
That is the MLCT band of the complex.
Why so?
That happens between the.
Is it depending on the solvent polarity? Have you tested that, or have you only measured in
No,
that
I just measure it in DCM, but it should be affected by the polarity of the solvent.
Okay.
So not affected by polarity?
Affected, it should be.
Okay. Then in this chapter, you mentioned also the formation of aggregates.
Yeah.
So general question is, what type of aggregates do you think they're forming in this case? And if so, how to characterize aggregates? Whatever you call aggregates.
So for the photophysical characterization, I mostly try it to avoid the formation of aggregates. So I always work in highly diluted concentration, but especially for platinum, when it's metal-to-metal interaction, I would say it's very easy to see it in the emission spectra because you always have an addition, like it's reported that when the distance between both platinum centers is shorter than 3.5 Armstrongs, you have aggregates, and this MMLCT transition is then available in the system, and you can see the formation in the emission spectra. So actually for 77K, that is why I changed the solvent, because when I was using DCM, the typical mixture that the lab used for characterize the molecules is DCM methanol to form the glassy matrices at 77K. And under that condition, I'll always have the formation of aggregates. So I saw always an additional band in the red region. And it's easy to see it because it's, I don't know, it's like at the end of the spectra in the red region. And when you measure the lifetime in that maxima is different that from the main maxima of the spectra, I would say.
Yeah, my
It's
question
another species and has another lifetime then.
Yeah, you mentioned you see a new band that corresponds to aggregate, but my question is what type of aggregates?
In which stretch? Like, I didn't.
What type of aggregates and how to characterize those aggregates? This will be my question to make sure that what you really see are aggregates or kind of assemblies.
I didn't follow all the photophysical experiments that I have are with aggregates. I measured the lifetime in each maxima to be sure that it was always monomeric species.
Yeah, but in some of the cases you see some changes in your absorption and emission that correspond to aggregates in chloroform, in DCM, in chapter 3.
Yeah, for the bis-tetrazole compound.
Exactly.
Just for the bis-tetrazole compounds, and it's caused because the planarity of the ligand of the bis-tetrazole is higher than for the other one. But to be honest, no, I didn't really characterize which type of aggregate was. I saw it in room temperature condition, but I couldn't avoid that formation.
Yeah, well, I know you want to avoid aggregation in this case, but sometimes it's hard to achieve.
Yeah.
So in such case, imagine that you need to characterize those aggregates. What other methods you will use? Spectroscopic or microscopic methods or whatever, would you use to characterize those aggregates to make sure that it's not, whether it's a dimer or a trimer or a polymer, or what would you use? Because the spectroscopy, the UV and emission gives you an idea about the packing of the molecules, the interaction of the molecules. Mm-hmm. But my question is, how can you know whether you have 2 or 3 or 100 molecules, or what type of aggregates you really have? What methods would you use?
For this platinum complex?
For in general, for anything that aggregates in solution.
So, at least in UV, typically you have new arising transitions, so you will see it. I assume you will see displacements of changes in the UV and emission spectra. So for platinum, I'm not sure, but at least with phthalate it's easier, no? Like when you have displacement to the blue region, you typically have H aggregate and the other way around, no? Like.
Yeah, my question is, how do you know that you have 2 molecules interacting in your aggregate, being the aggregate a dimer, or maybe you might have 3, or you might have 100 or 1,000. How can you characterize that? How can you estimate the number of molecules in an aggregate? I mean, if you think about microscopy, for example.
I don't know, like with DLS, maybe
DLS is
you are using nanoparticles.
Exactly.
I try to do it for the Laponite system.
Yeah, DLS is a good method.
DLS, maybe by TEM or something.
Yeah, exactly. Okay. Yeah, this is what I wanted to hear.
Okay.
So some characterization methods of aggregates. Then on chapter 4, you start talking about I can continue, correct?
Yeah.
Okay. You start talking about the phthalocyanines.
Mm-hmm.
I personally don't have experience with phthalocyanines. I have experience with other types of dyes, including porphyrins. And I know depending on the size of the metal ion, for porphyrins, the metal ion can be kind of buried in the cavity or can be kind of protruding outside a little bit.
Yeah.
Is this also the case for phthalocyanines? If you have large metal ions like platinum, they are in plane, or they are like a little bit protruding outside?
No, I think it can be a little bit of the plane, let's say it, out of the plane. And I think also the auxiliary ligand can play a role in the properties. I don't know in the planarity, but at least in the photoluminescent properties, the auxiliary ligand also plays a role.
Okay. Also in this chapter, this is a bit more challenging question. You speak about different types of exciton coupling in diaggregates.
Mm-hmm.
So you mentioned the 2 extreme cases, H-type aggregation and J-type aggregation.
Mm-hmm.
But there are some other intermediate cases that are not mentioned. Can you comment on that? Other types of arrangements of molecules that lead to different types of exciton coupling. that are not H are not J.
I think depending on exactly what substitutes you have here, you can have like kind of polymers between the microcycle, but I don't know if that counts like aggregation, but you can form like the arrangement between by functionalizing these positions and then building them like in series. And
But you mostly mentioned two cases, the H-type or co-facial arrangement, face-to-face, where the transition dipole moments are parallel to each other like that. Or if they are slipped, then you mentioned the J-type aggregates.
yeah,
But there are other cases. For example, if the two molecules are in a degree of 90 degree angle, something like that, like a cross shape.
okay.
Or it could be also that the angle is between 40 and 60 degrees. These are the other two known cases of exciton coupling. I don't know if you heard of that or not yet.
No,
Okay.
No, I didn't check that for
Okay. Okay, then to chapter 5. You calculated the number of molecules that are attached to the laponide. This is interesting. I don't know if this is too much or too few molecules. And I'm wondering whether is it possible to improve this loading on the laponide.
So I think, yeah, there should be some changes in the methodology, starting for the inert condition, for the stability of the molecules, and for the charging also. So officially the calculation is based on the volume of the molecule and from the laponide disc itself. So theoretically, if you put, even when you put more, it shouldn't, like by space, it shouldn't be able to put way more because it's anyway restricted by the surface of available of the laponide and the charge of the disc itself. So for some molecules, yeah, I had lower loading than for other ones. So I think that, yeah, there should be some changes. But I think the problems were, actually discussing with some of my colleagues, probably we could change the way of removing the washing of the laponides after the physisorption to decrease the amount of laponide, of the lysine that was losing within the washes.
Okay. Also in this chapter, you mentioned formation of aggregates of the laponide phthalocyanine hybrids. So once you absorb the phthalocyanine molecules in the laponide, then you mentioned the formation in some cases of H or J aggregates in some of the cases. You see some blue or redshift in the absorption spectra.
I think I don't have it here, but okay. Yeah, I know what you mean.
And I'm wondering if you have the laponide, which is a disc, functionalized with a few molecules. In some cases, you calculate, I don't know, 3 to 10, something like that. I'm wondering how this aggregation takes place. Is it between phthalocyanines that are attached to the surface, meaning intramolecular, or is intermolecular between more than one laponide that come together and phthalocyanines interact with each other?
So to try to avoid that, that is why I use 2 milligrams per milliliter, because when I did DLS of the laponide by itself. So when I had higher concentration of laponide, even when I sonicated, I will always have more than one population in the polydispersity. So I think I can show it. I didn't put it in the thesis actually, but I did the UV of the laponide and I did the DLS of the various concentration of laponide. So when I was having higher concentration of laponide, the polydispersity of the material was going higher. So that is why I always try to keep it low, but it's still sufficient to have a good emission, because also like when I had really low loading, I will have problems to detect the emission because it's already a small amount of molecules in the laponide disc, and then the radio of the dispersion, like the noise that the dispersion itself reflects in all the spectroscopy, is a problem already. And the most small laponide that if I had 2 less, I wouldn't see the photophysical behavior. And if I had too much, I will have always additional peaks. And actually, I have it here. I had problems also with reproducibility when I was starting to increase the amount of laponite disc.
So these are DLS experiments.
Yeah, so I will have it was just to check, exactly if I could control that they were reproducible, right? The behavior of the laponite in the water dispersion by itself is not loaded, but up to 5 milligrams, I still could have a good polydispersity index. But a part of that, I will have like really not reproducible, the standard deviation will go, and I will start having this raise here in the other population of the site. So that is why I keep it low to avoid as much as possible.
But these are not loaded with phthalocyanins?
No.
Okay. I was wondering how the phthalocyanins can interact and lead to the age of the J aggregates when you functionalize the laponites with the phthalocyanins. Whether it's, let's say, between laponites or of dyes that are
so
attached
typically
to
are bordered to phase due to the charge of the laponite itself, but once the molecules, the phthalocyanins are there, I'm not like in solution, I'm not sure, but I think that at least in the gel, it should be more or less the same. Otherwise, the gel wouldn't be formed.
Okay.
You need this ensemble to form the gels.
Yeah, I have to admit I'm not an expert in this functionalization of laponite, and I'm wondering about what would be the strength of this binding, because this is quite crucial for any in vivo applications. If you're going to use this at 37 degrees, for as you show it for MRI, or if you're going to use this in any animal model, I think it's important to understand what happens at 37 degrees. If there will be some release of the phthalocyanins.
Okay.
I don't know if this will happen. I have no idea.
I think it will be restricted by the solubility itself of the phthalocyanins, because once that it's onto the laponite, like they are not soluble. Like at least the ones that I was working with, they are completely insoluble in water. So it doesn't really matter how much you heat it up. Like 37 couldn't be enough to make it soluble in the water. So I think that once you have it out the system, it wouldn't go to water.
Okay. And we come back to aggregation. The next question will be again about the H-type exciton coupling. So you mentioned in several places of your PhD that H-type aggregates are to be avoided, let's say, because they quench the emission.
Mm-hmm.
My question is how to modify the molecules, your phthalocyanins, to avoid that. What would you do on the phthalocyanins to avoid the H-type aggregation?
Bulky substitutions in the rings.
Okay. But your phthalocyanins, they don't have any bulky substitutions.
No, but the terbutyls were bit better in aggregation already than the non-substituted. Actually, I started a project actually working with the non-substituted, and I had way more problems of solubility.
What is the best strategy in the literature regarding avoidance of aggregation of phthalocyanins? It's even led to a patent by Malcolm Kenny. It's even led to PC4, a photosensitizer for actual treatment of cancer in Canada.
Sulfonated?
No. It's axial substitution, silicon phthalocyanins. Nothing's better than that.
Okay.
Okay.
Should we get the ends?
I have a last question.
Okay.
Because you're using finally your hybrid materials for MRI. And Professor Cornelius Fava did already some preliminary studies, and I'm wondering whether you think about using this for any animal studies, for using any inflammation model or anything as part of the SFP where you can use MRI. First of all, and second point will be as far as I know, the density of the metals used in the material is crucial to have a good MRI signal.
What? Sorry.
So the density of metals, the number of metals that you use, the density of metals in the material that you use for MRI is crucial to have a good signal.
Yeah.
That's why mostly nanoparticles or iron nanoparticles are used, for example, for MRI.
Yeah.
I'm wondering what do you expect with your materials, because you showed already that your density of metals on the laponite surface relatively modest, I would say.
Yeah.
Do you expect, how are you going to improve that?
So I think that there first the modification of the loading to increase the amount. I didn't really go into that, but I really wouldn't say that the nanomaterials are functionalized because it's not doing chemistry on the laponite. It's just a physicization, right? It's not really doing chemistry. I will say that I could really do chemistry on the laponite to functionalize it, and then maybe try to increase the loading before going to animals. I will do that.
Yeah. Okay. Yeah.
Which type of functionalization, for example? I mean, Danny has presented some of his work, and he has explored possible functionalizations of laponites.
Kito-san? Yes.
No, Kito-san itself was a nanomaterial. Well, it doesn't matter. I will hand over to Jens now.
Yeah.
Okay. Yeah, thanks also from my side for giving your presentation of what you've been doing here during your PhD time. I would like to start but I would like to start with a few questions related to what you showed us today, and things that that maybe remained unclear or that I was thinking about when I saw those pictures. Maybe we can start with slide number 3. Can you go to 3? I think that was one of the overview slides. By the way, this is also a beautiful picture.
It's on my inventing.
Okay, here on the right hand side, your metallophilocyanine is C4 symmetric. So you only have the substitution, all substitutions are in exactly the same position. You mentioned in your thesis that in principle other substitutions are also possible.
Yeah.
So the question is, I think you also mentioned somewhere that the substitution pattern can be used to modulate the properties. So what pattern have you been using, and have you been able to show that the pattern has an influence on the properties?
So I think it's the other way around. So yeah, you have for the tetra substituted, you have at least 4 different isomers that can be isolated, but I think it's very hard to isolate them, and since once you obtain the mixture, it doesn't really matter that much. Like the substitution matter if it's either A position or alpha position or beta position. That is more important than if it's I don't know, like if for this one it will be here. Like it has been proved that between the isomers there is not really substantial difference in the photophysical properties, and basically that is not worth the work to isolate each of them.
But you're also adding, so when you say you did not isolate them, you took the mixture.
Yeah, you have the mixture, Yeah.
But you're also adding if I understood correctly, the reason why you added the substituents is also to improve solubility or to inhibit stacking or to modulate those interactions. Now, if you have different substitution patterns, I would expect that you may also get different propensity to stacking. Some may be better suited for stacking, or there might be better stacking between an alpha substituted and a beta substituted one, because then you might even get additional dispersion interaction. So was this ever studied? Not necessarily by you, but was this ever studied whether it's also in terms of stacking interactions and so on, it would make sense to separate them?
I think it's not really an influence. Like it changed from alpha to beta, but not between alpha. You know. So
I don't know the answer. You're the
yeah,
expert in psilocybin.
yeah, no, it doesn't really change.
Okay. Now that I also see here the leptonites very schematically drawn as discs, you mentioned on another slides that those are silicon-based materials. Maybe you can say a little bit more about how they look like chemically.
Yeah, can I put it in?
If you prepared it. You know, that's the only exam that you have where you can prepare your own sheet slides and even show them.
Yeah. So here is the whole composition of the laponite.
So what type of material is it? What's the chemical name for this type of material? Like silicone or silicate or?
Yeah, it's a silicone. It's silicone based that is here that forms a tetrahedral packing and here.
Yeah, but there are many silicon-based materials like silicones and silicates and silanes.
This is silicate.
This is silicate. Yeah. Okay. So, and why is it disc shaped? So why does it stop at a certain size? I mean, usually the silicates that are known from nature, they are like stones and not nice disc shaped. So why does the silicate suddenly stop? At 25 nanometers.
I don't know.
Okay. Maybe we go to some other slide. Oh, we are already at 63. Can we go back to 16?
Because it's the last chapter.
Those were the images of, I think those were where you had these STM images of your phthalocyanines. So what exactly do we see here? It looks to me like a nanoflower with 8 little white dots around a gray dot. So what exactly does this represent?
This is like a picture by the microscope taken of the phthalocyanide ring, and the dot is where they are putting the tip for the excitation of the molecule.
Oh, that's the red dot.
Yeah.
Yeah, but what exactly are the white and so why does it look like a flower? To me, the phthalocyanine.
The electron density is the electron density.
Yeah, electron density of what? Because the phthalocyanine has 4 big parts, right? So why do I see 8 small things? If this would be like the phenyl ring, or I should see they should be differently arranged. Again, I don't know the answer. I'm just curious. If it's the nitrogen atoms, they should maybe also be arranged differently. If you compare that with maybe you go to one slide where you just have the structure of a phthalocyanine.
Sorry, may I add to that? The answer is maybe found in why for zinc PZ it's even more than 1, 2, 3, 4 sigmoidal planes. The reason for that is on palladium you see the nodes, the nodal planes, and the lobes of the HOMO, of the LUMO of the molecule. And for zinc, the molecule due to the axial ligand is oscillating.
Oh, okay. So I don't see I see even more than the individual atoms. I see the orbitals.
Yes. Actually, the LUMO, because you're tunneling into the orbital.
Wow, that's cool. Okay, one synthetic question on slide 5. Why are you looking to the back?
Like nothing. Because they're on that way. To the 5?
No, that was not what I meant. Maybe next.
6.
6. Oh, yeah, I can't read my own writing.
It happens.
On the left hand, on the bottom of the left hand side, you have the symmetric substituted pyridine, and you react it with 5 equivalents of hydrazine, but you only get reaction on one side. Why? I mean, why do you only get reaction on one side and not on both sides? And especially, what do you do? Okay, I see it already. You'll probably take 10 equivalents to get both sides. So what? But I would say 78% yield for just one side is pretty good. So why don't you just use one equivalent to make sure that you get even better yield?
So yeah, So when I put less equivalents of bitresin, I don't get the full reaction, and that is how I actually isolate this one, because when I put less of equivalents, I just get the reaction.
And what's the other 22% that are lost? Is that already the one that has reacted on both sides? Or
Yeah, I can isolate both.
compound?
Yeah, but here, like, I see both in the DSC. I can see both and isolate both.
And on the top one, where you also have about 20% loss of yield compared to an ideal case, so that would be the monosubstituted.
I don't remember if so when I put less than 10, yes, I have a little bit more of this one, but I don't know if increasing this, yeah, probably would have.
Anyway, using a reagent in excess and still only getting a monosubstituted or reaction on one side is very helpful in this case, yeah. Well, maybe one more question that is not directly related to your own work, but you also mentioned that you use the laponites with your compounds on them as MRI agents. Why is there a need for new MRI agents? I mean, we just heard there are many other MRI agents, so why do we need more? Why do we need other ones?
I think before the gadolinium were very used, and now they are very, a lot of concerns arising. The concentrations of these related to fibrosis cases have increased. So they are looking for 3D, especially MRIs, that are based in more biocompatible metals that could be homeostatically processed by the body.
Yeah, that's correct. So why has there been the use of gadolinium, even though it's toxic? Even though it's known that it's toxic, why did people use gadolinium?
Because I think in that oxidation state have a lot of unpaired electrons, and it gives a really good signal, I would say.
Do you know how many electrons?
No, but I can see it very clearly.
How many oxidation states do you expect for gadolinium?
2+.
Is there any other you would expect? Yes, no, why? It's related to the question of the number of unpaired electrons.
I don't know the configuration specifically.
Do you remember which the ground state is of gadolinium 3+?
No.
It's an octet.
Okay.
It means it has how many unpaired electrons?
Is that V8? No.
I don't know.
Can I see it in the play?
Yeah, you can have a look at it very quickly.
I don't know what it is.
But
Sorry, no, it's
interrupt your
okay.
question.
Because then
We can
I mean, you already mentioned we need a lot of unpaired electrons for MRI, and gadolinium is the element which has the largest number, or where you can reach the largest number of unpaired electrons possible at all for one compound or for one element in the periodic table, and that would have been the question, or that is the question. How many electrons is that? What's the maximum number of unpaired electrons that one could use?
I can't find
You can't find it? Look at
But
very bottom.
I give you the answer. It's an octet ground state. So
Yeah, from octet ground state, you should be able to.
reduce the number of, and being an F block element with a
yes.
unique oxidation state.
It's in the lanthonide, so yeah, it will be 3+ mostly.
It's 3+.
Yeah.
It's F. How many F electrons?
7.
7, exactly. So it's a half-filled F shell. That's the most you can get in the periodic table among the existing elements, and that's why people have been using this. Would it also be possible in principle to make a gadolinium complex of the phthalocyanine? Just conceptually?
Yeah, I think so. But I don't know if it is.
It will give you a double decker molecule.
You know what is typically the coordination number of gadolinium in its complexes? How many atoms are binding, how many ligands are binding to it in a perfect gadolinium complex?
At least like 8, no? Like
Yeah.
a lot. Like
8 or 9, 9 is even better. So you want a lot. That's why phthalocyanine with only 4 will be difficult. That's why he talked about double decker. Exactly. Okay, that's it for me for now.
Okay, can you take over? Yeah. Okay, so I think it was slide 6 where you showed the synthesis. Can you give us an overview? What would be the reaction mechanism for the formation of the triazole? I mean, there are different synthesis steps. What would be the reaction mechanism that we would envision? Also for the click reaction. Because you have a click reaction for the formation of tetrazole. Let's start with the easier one. What's the mechanism of the click reaction for the formation of the tetrazole ring? Is it a cycloaddition? Is it dipolar?
I don't know the mechanism.
Okay. Also not for the triazoles. Okay. Good, then let's go more into photophysics, because you did quite a bit of photophysics and general physical studies on the different compounds. Is there a general physical tool named after a very famous scientist that you can use to describe the probability of STM, tunneling, absorption, emission, intersystem crossing, phosphorescence, fluorescence? What is the rule you would use to estimate the probability of a transition? It involves a matrix element, it involves densities of states. It's named after a scientist who also tried to estimate how high the probability is that we would be contacted by aliens. Yeah, it's an Italian scientist. Fermi's golden rule. Ever heard of that?
Mm-hmm.
Can you write on the whiteboard what the Fermi's golden rule more or less looks like, using a matrix element, density of state, just roughly? No. Okay. So in which part? I mean, the Fermi's golden rule basically gives you a probability of a transition of a time-dependent process based on a matrix element and a density of state at the state that you were going to reach. And within the matrix element, you have things like parity rules, transition dipole moment. For intersystem crossing, which is the major component determining the probability of intersystem crossing? The density of state refers on how flabby the molecule is in the triplet state that you're going to reach. But the matrix element, which gives you the quantum mechanical probability of intersystem crossing. For intersystem crossing, what is the main perturbation term in the Hamiltonian? It's not an electronic dipole moment, it's spin orbit coupling. The higher the spin orbit coupling, the higher the value of the matrix element. So if we talk about spin orbit coupling, you have used both light elements, let's say, like if we take your phthalocyanins, yeah, you have H2PC. H2PC has 2 very light atoms in the center, 2 hydrogen atoms. If we go to platinum, we have something very heavy. It's not the weight that is important, it's nuclear charge. which are the two types of spin-orbit coupling description that you know for light elements and for heavy elements?
Like the normal, the spin orbital coupling,
What's
and
the
the
name of
Russell-Sanders
Russell-Sanders,
for
exactly.
heavier atoms.
Mhm.
And
Russell-Sanders is for light atoms.
mhm,
It's a coupling of total L with
L
total
and
S.
S, no?
Yeah.
Mhm.
And for heavy elements,
Both the LS and the SL, the sum of both components,
for heavy
Yeah.
elements, you look at monoelectronic spin orbit coupling. So you look at the small L, small s coupling. What is that called? That type of spin orbit coupling? No, the Russell-Sanders is the big L, big S coupling. The heavier small L, small s coupling is called. It's related to Back to the Future movie. Relativity. It's relativistic spin orbit coupling. It disappears if you use Fermi-Dirac's formulation of quantum mechanics. And you have also discussed in your thesis some of the theoretical calculations that help explaining the, especially the copper phthalocyanine, which is, can you show again the Jablonski diagram for the copper phthalocyanine? The quartet states. Exactly. So right at the bottom, you mentioned DFT, TDDFT, and CAS. What's the difference between DFT, CAS, and Hartree-Fock? I mean, Hartree-Fock is a classical theoretical method that we learn in our undergraduate studies. Can you briefly say what's the difference between DFT and Hartree-Fock and coupled cluster theory? Or at least between DFT and Hartree-Fock? A self-consistent field. Okay. You have also used a cryostat, right? I mean, you used liquid nitrogen to measure glassy matrices, but you also used a cryostat downstairs, which theoretical. Do you remember what's the theoretical temperature it's able to reach? 4. Did it ever reach 4? No. What's the best you could achieve?
4.85.
Also with your PMMA films?
I always measure PMMA.
Okay, so typically you reach 6 or slightly below 6. Do you know which type of cryostat that is? Does it work with liquid helium?
No, with helium and the vacuum. It has 3 different, yeah.
But the helium circulating is not liquid.
No, it's in the content, yeah.
Have you ever had to refill the helium?
I don't think that it has ever been refilled.
No. Well, how are they called, these cryostats that do not need refill?
The system is, I don't know, closed system?
Closed cycle.
Yeah.
Do you know which type of helium cryostats allow you to reach millikelvin? It's a very funny thing when they do it. I mean, there are liquid helium cryostats that easily reach 4 Kelvin, but they are very expensive because you need lots of helium. Do you know which type of helium cryostats are used?
I think they have, like, at least for the STM, they have to fill it all the time.
Yeah,
they have to
that's
be
because
open,
it's liquid helium.
And they could go lower, like the STM that
but let's say
they have. It's
very crazy physicists that like to measure in the millikelvin range.
Yeah, like the STM, right? Like the STM is already at 4.
At 4, yeah, but if you go to millikelvin, so 0.02, 0.05 or something like that, you know which type of cryostats they use? They're called dilution cryostats. You take helium-3 rich, helium-3 poor mixtures with helium-4, and when they mix, the temperature drops a bit more. Okay, maybe to the general part, I have a final question. You know, in the periodic table of the elements, there are certain anomalies popping up every time a new a new type of orbital is filled. Weird things happen. For example, the 2p elements can make double bonds. The heavier elements don't do that. You have systematically studied a series of phthalocyanins with different metals. Can you maybe mention when you compare nickel, palladium, and platinum, which two anomalies show up?
For nickel, should be smaller than expected in the 3D. In
Yeah,
general.
and how does the 3D anomaly manifest in that case?
Treaty is less diffusive and it's very close to the center, to the nucleus in general, the orbital.
How is that reflected in the photophysical properties?
They are easier to populate. No?
Yeah, you have lower ligand field splitting. And which other anomaly manifests in that series, nickel, palladium, platinum?
Platinum.
Yeah. Which anomaly is that?
It has the F, this similar effect with the F.
And how does it manifest in there? Two manifestations of the 4F anomaly and platinum.
Mm.
I help you. Do you expect any significant difference in geometry or size between palladium 2 phthalocyanine and platinum 2 phthalocyanine?
Theoretically, platinum should be bigger, but it's not really the case, no? They are.
Exactly.
But it's because the F orbitals are very diffusive and there is contraction, no?
Yeah, the lanthanide contraction.
And that is why the size of all of them are smaller also than expected.
What other crazy stuff happens with platinum? I mean, if you compare, what is the change in nuclear charge when you go from nickel to palladium?
It should
How many protons?
increase, and for platinum decrease because.
No, the nuclear charge. If we look at the nuclear charge, the number of protons, how many protons are added when you go from nickel to palladium?
I don't know the atomic numbers, but it should increase, and then the nuclear charge.
I will help you. When you go from nickel to palladium, you have to fill, you have to complete the main group, and you have to add also the transition metal. So you have a jump of 18 protons. Now, if you go from palladium to platinum, how is the jump?
You have to fill the lanthanides, no?
So how many are they? How many protons?
10?
No, 14. 14. So you have 18 plus 14. So you have a jump of 32 protons. And that's why.
The nuclear charge increases and then they contract.
Exactly. And then you have the relativistic spin orbit coupling because of the very high nuclear charge. Okay, maybe you have still an open question for some? Jens, maybe? Some question?
Yeah, maybe one very general question regarding coordination chemistry. You mentioned in the introduction of your thesis that for the ligand field splitting in the square planar case, you kind of derive it from the octahedral case and say when you remove the ligands along the z-axis, then you get this the z square orbital lowers is lowered in energy, so that you essentially get the square planar ligand field. Now you said you need to remove them along the z-axis. What happens if we remove them along the x-axis? Would that lead to the same result, or would this give a? I mean, do we need to remove the ligands on the z-axis if we want to have square planar compounds, or can we also remove them on the x-axis?
As long as you move it from the same, like opposite side, so it
Exactly.
doesn't really matter, right? Okay.
Exactly. There's no naturally given z-axis, so it doesn't matter where you remove that. That's true.
I think it's just convention to do it in that one.
And one other question also, when looking at your introduction, it's on page 20. I read the sentence that you wrote, right? You wrote, knowing the oxidation state of the metal center, the nature of the ligands, and the geometry of the complex is crucial for determining the point groups, the molecule's point groups. So I understand why the geometry of the complex is crucial to determine the molecule's point group. But why is the oxidation state of the metal center relevant to determine the point group of a complex?
I think it's related mostly to the geometry that will be preferable, no?
Like if I think of iron 2 and iron 3, would you expect that the oxidation state influences the point group of the complex of the iron?
No.
No. So it's mainly the geometry. Maybe you meant that the oxidation state influences how many ligands are bound, and that will then be the geometry.
Yeah.
But I think the oxidation state alone is probably not relevant here. Okay, those were my two final questions. Thanks.
Okay, maybe one final question. You mentioned that intersystem crossing is neglectable for zinc PC. I don't totally agree with that. What's the fluorescence quantum yield of H2PC and zinc PC? Or let's take silicon PC. What's the fluorescence quantum yield? Is the system quantum yield for silicon PC as compared to zinc PC? You remember for zinc PC what the quantum yields are?
For fluorescence, very high, typically, but I don't know for fluorescence. I think
Okay. Okay, I'll help you. For silicon PC, you have 50% fluorescence, 50% intersystem crossing or singlet oxygen quantity. For zinc PC, it's only 30% fluorescence and 70% intersystem crossing. Can you imagine why that happens? Where do you expect more spin orbit coupling, for zinc or for silicon?
silicon,
No, for
No,
zinc
for
it's higher because it's heavier. That's why you have more intersystem crossing quantum yield. And okay, I think that's it from my side. Any other question from you? Okay, then we'll finish here. Thanks to all for attending the defense, and I would kindly ask everyone to leave the room now.
Can I give you a